All right, so this is an equilibrium problem, and we're given initial quantities, so we're going to start with an ice table. All right, so we're given our initial partial pressures of our two reagents. We assume we don't have any product, and partial pressure is good because we're given a value of Kp. Now for change, the easiest way to go about this is we'll have 3x, losing 3x of H2, and every 3 moles of H2 that we lose just 1 mole of N2. We determine this by looking at our coefficients, and we generate 2x moles of NH3. The equilibrium quantities are initial plus change. Right, so we've input our equilibrium quantities from the ice table into our equilibrium constant expression. And we would have a very difficult time, or a very long time, going through all the algebra and solving this cubic expression. So we're going to test to see whether or not we can make a simplifying approximation. All right, and looking at the simplifying approximation, what we're trying to determine is whether or not we can neglect the loss of 3x compared to 1,9 and x compared to 1.5. So we can introduce less than about 5% error if we multiply 1,000 times k, and that result is less than our our initial concentration. So we look at our initial concentrations, and they are both larger than 1,000 times k. So we can use our simplifying approximation. 1,000 times k is going to be less than our initial concentration. All right, so we're neglecting the terms here, minus 3x and x, and our equation reduces down to 4x squared. Note the 2x is inside brackets here. So 4x squared over 1.9 to the third times 1.5. All right, so here in this step here, we've multiplied 4.3 times 10 to the minus 4 times 1.9 to the third and 1.5. Here's our result, and that's going to be approximately equal to 4x squared. So now we solve for x. All right, so we finish solving for x. We find x is equal to 0.0253. That will carry that extra sig fig through the rest of the problem. Now that we have x, we can go back and answer our question, which is to determine the equilibrium partial pressure of our product, NH3. All right, and here we have our final answer. We went back and checked the equilibrium partial pressure of H2 and N2 and found that it did change a little bit relative to the initial pressures. So we have introduced a slight amount of error in making that approximation, but we're still within sig figs. And the partial pressure of NH3 is 2x, which is 0.051 atmospheres.